Now that we've seen how to find equations in three-dimensional space of lines and of planes, we can take one step farther and completely generalize quadric surfaces in 3 dimensions. So let's just start with recalling what the general form for an equation of a plane was. Right? For a plane, which is a surface, a two-dimensional subset of three-dimensional space is a surface. For a plane, we just had ax plus by plus cz plus d equals 0. This is a subset, right? And this gives you just sheets, infinite sheets in three-dimensional space, like in any direction you want by changing these values a, b, c, and d. Now, this is a small subset of possible shapes in three-dimensional space, right? There are spheres, paraboloids, ellipsoids, cylinders, tori, et cetera, like donuts, right? So, and we want to be able to define quadric surfaces. And let's just start with a definition here. Quadric surfaces are graphs of equations that can be expressed in the following form. In the form ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus, I'm running out of room here, hy plus jz plus k equals 0. So a lot of terms here, and you'll notice it's a quadric surface because the top degree of this multivariable polynomial is always 2. Here we have a variable squared. Here we have a variable squared, variable squared. Here we have one variable times another, but we're only taking the product of 2 variables, right? So this multivariable polynomial has max degree of 2, which is why we say it's a quadric surface. So any equation of this form represents a so-called quadric surface in three-dimensional space, where the capital A, B, C, etc. up to K, excluding I, these numbers can vary, and they give us different surfaces based on the different values, right? And so for the plane, right, the plane, equations of planes are a very small subset of quadric surfaces, because for a plane, A, B, C, D, E, and F were all 0. For a plane, we were just looking at this here, right? And now we're kind of flinging open the door and saying, like, what can we have that defines a surface? And so the first question, a pretty natural progression, is to say, okay, so if I'm given one of these equations, because there's a lot of, certainly infinitely many equations of this form, how do I know what the quadric surface is going to be? Like, what's the graph going to look like? Just because I'm given an equation, great, it's a quadric surface. What's the graph going to look like? And that's what we'll spend a lot of time on talking about today is, okay, here's an equation, or here's a certain type of equation. What is this representing? So how do we graph quadric surfaces? Well, there's a very, very useful technique, and it's called using a trace, or using technique here. is to use traces, so-called traces, right? And so formally it's called a trace. Informally, it's a two-dimensional slice. So what do I mean? Let's look at a sphere in three-dimensional space. X, Y, Z. Here's our coordinate system. And let's say we have a sphere. Here's our radius. Here's the top of the sphere. Here's the bottom of the sphere. Okay. And we want to calculate the traces. There's three main traces that we're interested in. So three main traces, namely a trace parallel to the XY plane, the XZ plane, and thirdly, the YZ plane. So what we're going to restrict our attention to is not just taking like any old plane and intersecting it. You can certainly, and maybe in some cases that's more beneficial. But in general, it suffices for us to be able to put the picture together to just consider the trace of, or taking a two-dimensional slice of our surface that's parallel to one of the three coordinate planes. So let's look at a trace just for an example. Let's look at a trace parallel to the XY plane, right? So you can see the XY plane is, it's an infinite plane, but it goes in this direction. It's kind of flat, if you will. If we take a trace parallel to the XY plane, we're going to take a horizontal slice out of our sphere and look at what the two-dimensional picture is. If we take a slice, a 2D slice or a trace, and map out what the picture is, it's just going to be a circle, right? If you have a sphere and you take a slice of the sphere and you just look at that slice, like that level, what is a sphere, right? Well, it's just a circle. So the trace here, and if you will, this lies in the XY plane because we're taking a slice parallel to the XY plane. The trace is just a circle with radius, whatever the radius or whatever this distance is. If it's at the equator, then it's the radius, right? If you take a slice higher up, like maybe near the North Pole or something, the distance is going to be smaller, right? But you get some distance r. And so we see the trace parallel to the XY plane is a circle, right? And you can do the same thing for the YZ plane and the XZ plane. So what if we took a trace of the XZ plane to take something parallel? Well, the XZ plane is this plane here in green, right? If we took something parallel to the XZ plane and took a slice out of it, what would be something like this here, and we took a slice, you can see now, instead of getting a circle that wraps parallel to the equator, we'd get one that wraps kind of north-south around the north and south poles if we took the trace. But still, the trace, so here, let's say this is the XY slice. That's not really a coined term or anything, but I'm just going to call it that. Now we're taking the trace, and this is going to be the XZ slice. And lastly, we could take a trace and look at the YZ slice. And so what would the YZ slice be, right? It's going to be a copy of the YZ plane. Well, the YZ plane is kind of consistent with the screen we're looking at, right? So if we took a slice, kind of, you'd think about slicing the sphere. If you're like looking at a sphere and you have the basketball, you'd think about slicing it like just right through, parallel to our screen, right? And so that's what a YZ slice is going to look like. And if you take a YZ slice here and look at the intersection of that slice and the sphere, you notice, again, we're just going to get a circle. And so what you have to do is kind of look at all like these different coordinate projections, right? You look at like, what does the sphere look like projected onto the YZ plane, or projected onto the XZ plane, or projected onto the YZ plane? You have to look at all these projections. And so you get an idea of the two-dimensional slices of this surface, and then you try to piece it all together and say, okay, here's my quadric surface. And in this case, it was a sphere. So next, let's look at another example that's maybe a little more complicated than a sphere, because, you know, in a sphere, you can slice it any way you want and you get that a trace is a circle. But let's do a different example, one that's a little different. Let's look at a cylinder here. If we look at a cylinder, say here's like X, Y, Z, and let's say we have our cylinder of radius R. Right, cylinders have a radius, and it's an infinite cylinder, excuse me. So it goes on infinitely. And let's say it's oriented in this way. Let's say that it's centered at the origin, if you can see the picture there. And so now we have our infinite Pringles can, and we want to determine what the traces are. So let's look at the XY trace, or the trace, to be more formal, let's say trace parallel to XY plane. I'm going to shorten that notation and just say like XY trace, meaning we're taking the trace of a plane parallel to the XY plane. And so what are we going to get for a cylinder, right? We take something parallel to the XY plane here, and we look at a slice. So imagine taking a Pringles can, you slice it in like a really, really thin piece, right? Say you slice this Pringles can twice and you have a really, really thin piece left over. And you say, okay, what's the shape of this piece left over? Well, if you slice it in the XY plane, you'll see that it's just a circle of our fixed radius, right? A cylinder has a fixed radius. You can take this slice at any level you want, right? So, and it's going to have the same radius when you take that slice. And notice here, I'm mentioning height. When I take something parallel to the XY plane, that means I'm taking a slice. I'm taking a slice at Z equals some constant, right? Say I'm marching up K units in the Z direction, and then I take my slice. That's a trace parallel to the XY plane. And the equation of the plane that I'm taking a slice is given by Z equals K, right? And so now there are two other coordinate planes that we can look at. Let's look at the XZ trace, right? And the XZ trace is now, I'm taking something parallel to the XZ plane. So I'm looking at some Y distance, some fixed Y value, and then taking a slice. So this would be at like Y equals, so here this is Z equals K. Let's call this one like Y equals, well, I'll call it K1. How about that? Some fixed distance. Here's Y equals K2. And so we're marching like K2 units somewhere along the Y-axis. And now we're taking a slice parallel to the XZ axis. And so if I take a cylinder, right, like a Pringles can, and I slice it in a way that's like perpendicular to the screen you and I are looking at. If I take a Pringles can and I slice it and I look at the little thin slice, what do I have? I have two disjoint components. I have two lines, right? If you take the XZ trace here, you're going to march out however far the radius is. And I have two lines like this. This is the XZ trace. Well, let me draw it in green since I've been trying to be color coordinated. And this, for a cylinder, this is the XZ trace. It's these two lines, because if I take a plane and slice it through this cylinder, where does it intersect? It intersects at this line over here, and it intersects at this line over here. And that's the only place that my graph intersects. So the trace, or the two-dimensional projection, is just two disjoint lines. And so this is what it'll look like in the XZ, or in an XZ trace. Now, what about a YZ trace? Now I take a plane that's perpendicular, or excuse me, that's a parallel translation of our screen, right? The YZ plane is on our screen. I'm taking a parallel translation, and then I'm taking a slice. And well, you can see if I do that, so let me draw another cylinder here. And now if I take a slice through it, parallel to our screen, right? This is a YZ slice. What do I get? Where does this intersect? It intersects at two lines again. And so, and those lines, right, from the origin, they're both out a distance of the radius. And so this is my YZ, a trace in a plane parallel to the YZ coordinate plane. And so you can kind of look at these three two-dimensional pictures, right? We have 1, 2, and 3. And you kind of look at all three of these and say, okay, well, if I piece these together, then here's the given shape I get. And just for the sake of completion, here I was saying, you know, when you take an XY slice, you're looking at some plane given by Z equals a constant. If you take a XZ slice, you're looking at a plane given by Y equals a constant. If you take a YZ slice, you're looking at a plane given by X equals a constant, maybe K3, right? Because if we draw a coordinate system in here, say X, Y, Z, then I want something parallel to this blue plane here, which is corresponding with the YZ plane, right? That's just translate, like I'm just making X values bigger or smaller here, and then taking a slice of this plane. So that's an idea of traces. So now let's go the other way, right? The first two times I was like, here's a sphere, what are the traces? Here's a cylinder, what are the traces? But in the quote unquote real world, it'll be the other way, right? You'll be just given like a function, and you have to first find the traces based on the function, and then use the traces to piece together what the quadric surface looks like. So let's look at an example here. Let's describe the traces of the elliptic paraboloid given by x squared plus y squared over 2 squared equals z over 5, right? This defines some quadric surface, and we want to be able to give a sketch of this graph to see what kind of shape we're working with here. So let's compute our traces, right? There are three traces we need to compute. We need to compute like a quote unquote XY slice. And so we'll want to look at a plane parallel to the XY plane, and then we'll slice this surface and see what we get. Well, an XY slice corresponds to, remember, z equals some constant. And we have freedom to choose what this constant is. Usually you want to pick like 0 or 1 or whatever is the most convenient. If we pick z equals 0, well, then we have x squared plus y squared equals 0, or x squared plus y squared over 4 equals 0. The only solution is the point 0, 0. So if we take the slice z equals 0, we just get a point at the origin, which is nice to know, but it doesn't tell us enough about like what a general slice in the xy direction is going to look like. So let's take something non-zero, but that's a little more convenient. If we pick z equals 5, this gives us an xy slice, and it makes the equation a little nicer, because the equation then becomes x squared plus y squared over 2 squared equals 1. And this is an ellipse with semi-major axis 1 and semi-minor axis 2. So 1, 1, 2. And we can see this looks pretty circular, but it should be an ellipse. Let's just redraw it. So here's x, here's y, 1, 2. This looks a little more elliptic. And so this is our xy trace, right, is an ellipse. It means, so whatever our surface is, when we take a two-dimensional slice parallel to the xy plane, the result is an ellipse. Okay, that's interesting. So now let's see, that was the first trace. What's the second kind of trace we could do? We could do an xz slice. An xz slice is when y is equal to a constant. And then we're looking at the xz plane, xz plane. And so when y is a constant, let's remember what our function is. I'll just copy it. It's x squared plus y squared over 2 squared equals z over 5. Okay, and so if y is a constant, well, now would be a little clever to just pick y equals 0, because we can see it still gives us information, like the function or the resulting formula is still non-trivial. So if we pick the slice y equals 0, this is exactly the xz plane. So we're not even taking a parallel copy of the xz plane. We're looking at a slice of the xz plane itself. And we get x squared equals z over 5, which gives us that z equals 5x squared. And so this is a parabola. So we go 1, 1, 2, 3, 4, 5. And we have the parabola z equals 5x. So in the xz slice, if you look at a slice in the xz plane, we get a parabola. So that's interesting, because now we need to think about kind of geometrically, okay, well, we have an ellipse in the yz plane, but then we have a parabola in the xz plane. And so we have 2/3 of the picture here. Let's put the rest together. What about the yz, or a slice parallel to the yz plane? Well, this is when x is a constant, right? And so again, let's just let x be 0 here, because plugging in 0 still gives us useful information. If we plug in x equals 0 to the original function, then we have y squared over 4 equals z over 5. And it looks like we'll have z is equal to 5/4 y squared, which is another parabola, right? It has a kind of a different pitch, or slope of the opening is different, right? And it's almost 1-to-1. Or, I mean, it's almost 1 and 1, but it's 1 goes to 5/4. And this is in the yz plane. And so now we need to think about putting these pictures together, right? And let's take a look at all of these pictures at once. Just a sketch. Here's xy. We have an ellipse. here's xz. We had a pretty steep parabola. And then here's yz. We had a parabola that's open a little more. So these are the three traces. And now we need to say, okay, well, what does this give us as a surface? And here's what we can do. Let's draw our three planes. Here's the xy plane, right? Here's then the xz plane and then the yz plane. And so let's just kind of draw one of our traces at a time here. In the xy plane, we were at the height z equals 5. So let's trek up 5 units, right? Because we need to remember where we were at when we did this. We were at z equals 5. And remember, if we plug in z equals 0, then we just get x equals 0 and y equals 0, right? Because that's the only solution. The sum of two positive numbers is 0, if and only if each one are 0, right? Because they're both positive, so they can't be the negative of each other. So that means we have the point at the origin, which is nice, and we know we have nothing under it because these are all squared numbers, which means they're all positive. So we can look purely in the top 4 octants. We're at the level z equals 5, and our trace was an ellipse. So something like this. Here's the trace in the xy plane. Now we have a trace in the xz plane. The trace in the xz plane was a parabola. So that means we have something that looks like this, right? Where that's purely like in the xz plane, which is to be perpendicular to our screen, right? And then the yz plane should correspond with our screen. And so what about in the yz plane? Well, in the yz plane, we have another parabola like this. And now we have 3 traces, and we can kind of put the picture together here. Say, okay, we just kind of fill in the rest. And you can see this generates what's called an elliptic paraboloid. And it's like an infinite bowl that opens. You can kind of think about it like a parabola, but you rotate the parabola in the 3rd dimension, and you get like this infinite bowl, which we call an elliptic paraboloid. And so this is how we can use traces to find sketches of our surface. So this is the surface, x squared plus y squared over 2 squared equals z over 5. Here's a sketch of the elliptic paraboloid. And that's really what the problems from this section are about, is getting familiar with how to use traces and then how to piece them together in the 3rd dimension to get a sketch of what geometric surface or what quadric surface this is representing. And so to wrap this video up, I'm actually going to hop over to the OpenStax textbook because they give a nice, concise kind of generalization of quadric surfaces here. So let's take a look. Here you can see we have our quadric surfaces generalized by this formula, right? Which we've gone over. And now let's just kind of look at some of the basics. So, and just so we can get like some definitions and vocabulary down for certain types of shapes. So we've seen like cylinders and we've seen spheres, and spheres are a subset of ellipsoids. See, if A, B, and C are all the same number, then this surface is a sphere. Okay, and so an ellipsoid is basically like an oblong ball in 3 dimensions. Think about like a football maybe, but not with the pointed ends, right? With like a rounded with rounded poles, right? And so you look at the traces here, and you can see like what's an XY trace, right? Well, an XY trace is going to be something like this, which is an ellipse. You can look at an XZ trace. Let's use a different color, one that'll show up here. An XZ trace is going to be like a longitudinal line, right? And like the XY trace was like a latitudinal line. And then we could look at also like the YZ trace, which is also a longitudinal line, but at kind of like a pi/2 rotation of the first, right? And so we can take a look at these traces here and see that, okay, well, in each trace is an ellipse, and you can see all traces are ellipses. So putting that information together, we know that our surface must be an ellipsoid. Let's take a look at the next one. So here we have hyperboloids of one sheet and of two sheets. So let's start with just a hyperboloid of one sheet. If you take something parallel to the XY plane, notice at any height, you just get an ellipse, kind of that would wrap around back here, right? You can look anywhere, and at the center, we have an ellipse. We have an ellipse, right? These are all slices or traces in planes parallel to the XY plane. And now what's a trace parallel to the XZ plane, right? We can see it's going to be these lines here, like these outward bending lines, and like the trace would be like back here for this one, right? And so these are hyperbolas, right? When you have a line, two lines like this is a hyperbola. Or let's just use this. Right, and so we can see an XZ trace is a hyperbola, and then also a YZ trace is a hyperbola. Because again, you just take this hyperbola that you got from the XZ plane and rotate it by like pi/2 radians, and you take a slice kind of parallel with our screen here, and you can see you just get another hyperbola. So if you have like that two hyperbola, if you have two of your traces are hyperbola and then a third one is an ellipse, you get that it's a hyperboloid. Now, the difference between a hyperboloid of one sheet and a hyperboloid of two sheets is what happens in the middle. If you hit somewhere where the trace is the empty set, right here, for a hyperboloid of two sheets, you can pick p-values, or excuse me, you can pick z-values, where if you take a slice parallel to the xy plane, you get nothing, right? That's when you have a hyperboloid of two sheets. If you get an ellipse for every value of z, then you have a hyperboloid of one sheet. And you can see like the difference here is like, you know, there are two disjoint components. Like this graph is not connected, right? Like there's no surface between these 2 points, but here there is surface between these 2 points, which means this is a hyperboloid of two sheets and this is a hyperboloid of one sheets. And again, the difference is because they'll look the same in terms of traces if you pick the right z value. And here's a telltale sign. A hyperboloid of one sheet has a plus and a minus, whereas a hyperboloid of two sheets has two minus signs. So that's kind of a telltale sign of knowing when your quadric surface is a hyperboloid of two sheets or of one sheet. So now let's look at some more here. Here we have an elliptic cone. An elliptic cone is, we can look at something parallel to the XZ plane, and we see we have an ellipse, right? If you take a slice of this, of these cones in the XY planes, you're going to get ellipses. And then otherwise, like in both the XZ and the YZ planes, you're going to get hyperbola that look like that. Here, blue's not a very good picture. Let's do like lime green. You're going to get hyperbola like this. Now, how you know it's an elliptic cone is you look at the XZ plane and the YZ plane itself, and you look at the trace there. There, the trace is a pair of intersecting lines. You can see, like, what I'm drawing in green is the YZ plane. The intersection of the YZ plane is these two lines here that intersect at the origin. And then if I were to do like the XZ plane, it would be like this line, then that goes through to the back, and then like another one on the back side of this cone. So it's making like another X shape, but now perpendicular to the screen. So you can't see the X, you can just see like the ends of the X, right? Next, we have an elliptic paraboloid, which we just saw, right? It's something of this form here, where the trace parallel to the XY plane is an ellipse, and then the other two traces are parabolas, right? Something like this. It's clear. And the last one would be a hyperbolic paraboloid. And so this is something where you don't have any ellipses whatsoever. You have in, if you take a slice parallel to the YZ plane, you have a hyperbola, right? You get like two lines, like here and here. You can see how that's a hyperbola, right? Because I have two lines that are kind of bowing out away from each other. And then the other two, the XZ plane, I'm going to get here. For the XZ plane, you can see I'm getting like downward facing parabolas, right? That I'm drawing in green, like these here that are opening downwards. And then for the YZ plane, you have parabolas that are opening upwards. So you get these parabolas. And so here's just kind of a small set of important quadric surfaces that I think will be useful when getting familiar with identifying traces and identifying surfaces. So this wraps up kind of our talk about equations of subsets of three-dimensional space, namely quadric surfaces, right? And first we talked about planes and lines. Next, before we can get to multivariable differentiation, which is one of the bigger topics of the course, we first need a little bit of background information about vector valued functions. And so we'll be discussing those in the next video.